Welcome. In the last lecture, we posed ourselves a question: if n is factorized with m and m prime, and if my f is defined in terms of f is defined from z m prime to z. So, this is what we have said, and we would like to compute the Fourier coefficient of this g in terms of the capital F. So, now this I can put it as a theorem. So, let capital N is equal to m into m prime, and F is from Z n by m to C. Define G of n is equal to f of n by m, n by m for n is equal to 0 plus or minus m plus or minus 2m and like this, and 0 otherwise. Then g of k is equal to 1 by m f of k. Second also, if I define g of n, if g of n is equal to f of n, remember that up to m prime minus 1 there is no problem. So, if n is greater than, so which means if we are taking, suppose say n is equal to 4, m prime is equal to 2, then so g of 0 this is equal to f of 0, g of 1 this is equal to f of 1. Now, g of 2, now 2 is going to corresponds in Z 2 as 0. So, I will define this as f of 0, and g of 3 is f of 1. So, this is what is the meaning of f g of n is equal to f of n. Then g of k, this is equal to f of k by m if k is equal to 0 plus or minus m plus or minus 2m and so on and so forth, and 0 otherwise. Okay. So, this, so let us prove this. G of k if I take, then this is equal to, by definition, 1 by n summation over n is equal to 0 to n minus of 1 g of n e to the power minus 2 pi I k n by n. Now, g of n is defined like this. So, this we can write is that summation over 1 by n, then this is when n is divisible by m, g is taking non-zero value, otherwise it is taking the 0 value. So, now this is equal to, I will write it at n prime is equal to 0 to n by m minus of 1 f of n prime, then e to the power minus 2 pi I k, this n is equal to m n prime. So, therefore, this is m n prime divided by n, and this one is going to be, now n is equal to m m prime. So, now this is 1 by m into 1 by n by m summation over n prime is equal to 0 to n by m minus 1 I k, and this is n prime divided by n by m. So, this is nothing but the Fourier coefficient of f. So, just writing it down, one can easily get this. Now, for the proof of 2. So, this is summation over n equal to 0 to n minus of 1. Let me try g k e to the power 2 pi I k n by n. This by Fourier inversion formula, this is g n. Now, in our definition it is f n. Now, if I want to put the Fourier inversion formula over here, so this is going to be summation over k is equal to 0 to n by m minus of 1 f capital F of k and e to the power 2 pi I k n is here divided by n by m. So, now equating the coefficient of this, now what do we get? We get that g of k is equal to, let me denote this to be k prime, k prime, k prime is equal to f of k prime if k prime of m into n, this is equal to k n. That means, this is equal to what does that mean? That means, k prime is equal to k by m, and that is what we would like to get, k prime. So, hence g of k is equal to, and otherwise this is 0, g of k is going to be 0 if it is not of this form, because they are linearly independent. So, therefore, what we get is that this is f of k by m if k is equal to, whenever k is divisible by m and 0 otherwise, just with the comparing the coefficient. Okay. So, now let us see some interesting example based on this observation. So, which is going to be very useful in certain aspects of mathematics and its application. So, this is let us say look at a concrete example. Let f is from Z4 to C. Now, G I am taking from Z8 to C. Now, what I define, let us say G of n, this is equal to f of n by 2 if n is even and 0 otherwise, because 8 is 2 times 4. So, our m prime is 4 and m is 2. So, then how does this map is going to look like? If I have f of 0 is some a, f of 1 is b, f of 2 is c, f of 3 is d, then g is going to be defined as g of 0 is equal to a, g of 1 this is equal to 0, g of 2, this is equal to f of 1, which is equal to b, g of 3 is equal to 0, g of 4, which is equal to c, g 5 0, g 6 d, g 7 is equal to 0. So, this I can write this as if f a b c d, then what we get, our g is equal to a 0, b 0, c 0, d 0. If now let f of a is equal to a, capital F at Fourier coefficient, because this is going to be again in Z4 d. Then now if I write the Fourier coefficient of g, this is going to be 1 half 1 by m, m is 2, and then the one by 2, and then this is a b c d again. Now, g of 5 what we are going to look at. So, this is going to be a b c d, because as you can see what we have derived is here this is defined in this way. So, now this is g of k equal to 1 by m f of k, there in that case m is 2. So, therefore, now 5 will correspond to Z 4, 4 is going to correspond to 0, and 5 will be correspond to 1, 0, 5 is correspond to 1, 6 is correspond to 3, and 7 is will correspond 2, and then this d is going to correspond to 3. So, similarly, if I define my f a g to be, let us say I will add 2 more zeros, b 0 0, c 0 0, and d 0 0. That means, I am looking at Z 12. Now, here m is 3, therefore, now this g is going to be 1 by 3, then a b c d, a b c d, a b c d. So, now for the other part, if we would like to define our g to be a b c d, a b c d, that means g of n is equal to f of n. This is what corresponds to g of n is equal to f of n. Now, in this case, if I by what we have derived in the theorem, let us write down the g. G is going to be, if it is k by m, if k is of the form plus or minus m and 0, otherwise it is 0. That is what the g of k would be. So, the first one is a, then I have 1 is 0, because it is not divisible by 3. So, now this is going to be b 0, c, there here m is 2. So, 0 and d 0. So, 6 I will get d, that is f of 3, here 4 f of 2, in the case of 2 f of 1, that is b, and 0 case f of 0, capital F of 0, that is a, and the rest of the things are 0. So, now this is, you can see that, I mean, if I am going to put certain, just if I want to extend my function from one finite group to another multiple of n, then essentially when I am computing the Fourier transform. So, on the places I am going to fill up the places either by 0 or repeating the Fourier coefficients. So, another interesting observation one can also get, I will write it in the form of the proposition. So, let f from z m into n to c and g I am defining from z n to c, the other side. So, here f I am been given with some, let us say 2 n, and g is a function from n to c, then what is going to be the Fourier transform of g vis-a-vis the given Fourier transform of f. So, 1, if suppose g of n. So, what I am doing is some sort of the periodization such that I will get into m into n. So, now this function, if I am defining to be L is equal to 0 to m minus of 1 f of n minus ln. This is a periodization. So, now then g of k, this is going to be m times f of m k, and then the second one is that if g of n, this is equal to f of m n, then g of k, this is equal to summation over L is equal to 0 to m minus of 1 f of k minus L n. Okay, so, what is the proof of this? So, now I write 1 g of k, this is equal to 1 by n summation over n is equal to 0 to n minus of 1. This is g of n e to the power minus 2 pi I k n by n, and we know the formula from 1 by n, and this, if I put the value, this is L equal to 0 to m minus of 1 f of n minus L n, that is the definition of g, e to the power minus 2 pi I k n by n. Now, recall that e to the power 2 pi I, any integer, that is going to be 1. So, therefore, this I can write this as 1 by n summation over n is from 0 to n minus of 1 summation over L from 0 to m minus 1 f of n minus L n into e to the power minus 2 pi I k times L minus n minus ln divided by n, because ln by n is L and e to the power 2 pi I k L, this is nothing but 1. So, therefore, I can write this. Now, these two sums, if I am writing, then this is going to be 1 by n, combining these two terms is sum n prime. This is equal to 0 to m n minus of 1 f of n prime e to the power minus 2 pi I k n prime by n. So, this I can do this as I will multiply m by m. So, this I can now again I can write this as m n prime by m n, m m gets cancelled. So, this is 1 by n. So, I want a factor of, so this I can write m into n m. So, this is nothing but the Fourier coefficient of f, that is what we want to prove, f of m k, because this is the m k is coming. Okay. So, exactly in the similar fashion one can get that the second part of this. So, which if you do the breaking up the sum like this, you will get the second part proof. Is similar. Now, so it will be interesting. The interesting question is going to be that how efficiently we can compute the Fourier coefficient in a finite group in Z n. That is what how many, that is what it says, that finally if we ask the computer to compute the Fourier coefficient, then how many steps it requires. Now, let us try to understand this problem. So, now what we want to get is that we have a function f from Z n to C, and we are denoting the Fourier coefficient of f is, this is again a function from Z n to C. So, we can, that means we are defining f is equal to Fourier coefficient, just I am changing the symbol, this is what we. So, now let us look at my f. This is equal to the column vector f of 0, f of 1 and f of n minus 1, and capital F, this is going to be equal to f of 0, f of 1, f of n minus of 1. Now, I need to find a matrix script f, which is going to give me that if I act on this f column vector, I am going to get capital F, the Fourier coefficient, again the column vector. So, I am looking for a n cross n matrix, which is going to give me the Fourier coefficient. Let us take, let omega is equal to e to the power minus 2 pi I n by n. So, now let us look at, so what is our Fourier coefficient? Fourier coefficient, let us 1 by n summation over n is equal to 0 to n minus 1 f of n e to the power minus 2 pi I n k by n. This is what we would like to see. So, now this is no n. Now, consider the matrix F is 1 over n, 1, 1, 1, 1, 1, 1, 1. This is omega, this is omega square, omega to the power n minus of 1. This is omega square, omega to the power 4, and omega 2 into n minus of 1, and this is omega n minus of 1, omega 2 times n minus of 1, and omega n minus of 1, n minus of 1. This is what we have defined. Now, if I compute f acting on f, then this is going to be f 0 to f n minus of 1. Now, this is summation over f of n, n is equal to 0 to n minus of 1. So, now if k is equal to 0, then this is what exactly what we have got. So, this is nothing but f of 0. Now, in the second row, if I am multiplying it, then what I am going to get? I am going to get f 0 plus f of 1 into e to the power 2 pi k is 1 I divided by n plus f of 2, and this goes on up to f of n minus of 1, then this one is omega e to the power 2 pi I n minus of 1 by n, and this is nothing but f of 1. And so, if you do the last one, so this is f of 0 plus omega to the power n minus of 1 means e to the power minus 2 pi I n minus of 1 by n. So, now that will corresponds to f of n minus of 1. So, now this is equal to f just by the matrix multiplication. Now, this is that. So, how many arithmetic operation we are now doing to compute all the Fourier coefficient given a function f. So, what we are doing is that now multiplication of the n cross n matrix is going to give all our Fourier coefficient. So, which means on each of the thing I am multiplying n times and adding n times, and so there are n such columns. So, it is something of the order of n square. So, now if I am going for a large z n, for n large, then the computation is going to be n square, kind of order of n square, which is pretty big. Now, the question is that can we reduce this n square to a lesser quantity? Can we calculate the Fourier transform more smartly, so that we will require less number of steps? So, that we are going to see it in the next lecture. Thank you.